Welcome, everybody. Today, I want to give you an introduction to engineering agents from prompts to loops. And we're going to do this using an example of a forecasting agent. So my name is Stefan Jansen. I'm the author of the book Machine Learning for Trading and also the founder of Applied AI. We have been implementing production solutions for ML and AI since 2015, and in some cases even before that. So I've been around for quite some time. The book has just gone live a few days ago. This is the third edition of the book Machine Learning for Trading. 800 plus pages with a lot of additional material around them. Including an agent lab, which we'll discuss in a second. There's also a comprehensive repository with some 450 notebooks that comes with this. That's freely available under my personal GitHub that has over 20,000 stars, so it has become quite popular. So I'm giving this talk and offering a workshop on this topic because I've been working with agent engineering for some time in different domains, healthcare, insurance, and investment. And the book contains a new chapter on autonomous agents that explains how to implement them. And that's what I want to discuss today. So we will introduce what an agent actually is, how it works as an LLM in a loop that can call tools and do other things, and what the key decisions for you as an engineer really are. And you probably have followed the discussion that has emphasized that we engineer prompts and context and a harness and more recently loops or maybe even graphs. So the discussion has evolved just as have agents rapidly over the last year. What we discuss is how each of these four areas and the decisions that you take there make a specific, take a big agent and help construct a forecasting agent that you can actually run live. Now, this is a specific example, the forecasting agent. In reality, we can build many different agents, such as this forecasting agent, using this approach. And this is where this is useful. And there will be a workshop where you can actually build the agent end to end, and not as a toy example in your notebook, but as something that you can actually deploy in production, as we will see in a minute. It runs live on our website. So what is an agent? Much discussed, an agent really is a large language model that runs in a loop with the ability to call tools, produce results, process the results, and repeat. So rather than your chat, GPT, etc. interface that represents a chatbot where it's a single turn, which may use agents to produce the answer, but your experience is one of back and forth. An agent is driven by a model and can act to achieve a goal, right? So your job as user or engineer is to define a goal and then create an environment for the agent to successfully accomplish that goal. In order to do so, the agent will call tools, read the results, decide on the next move, and ultimately also needs to figure out when it has achieved its goal, which is not always all that trivial. So there's a basic model behind this, which is the reason, act, and observe loop that has much discussed. That's just a conceptual kind of framework. But what's really important is the kind of environment that you construct around this. So the basic flow that you engineer is an LLM that receives inputs, which may be your prompt. It may be some external input, a call from an API, a file that it reads when it arrives. And it reasons over this input, and it can decide, do I need more information? What else do I need? What could be my next steps? And this depends, of course, on the actions and tools that it has available. And it can then select the tool and invoke it. And many different tools exist. Of course, web search. In the forecasting agent, it might be interesting to use additional data, external data, internal data. May use a calculator. It can use many different things, right? It can use a sandbox to create and execute code. So lots of abilities that you as an engineer can give to an agent for it to enrich its ability to obtain information and achieve its goal. And then it iterates. It acts, calls a tool, obtains a result, reasons over the result. Does it match the goal? Does it mean the loop can exit? If not, it repeats. So how do you go about this as an engineer? As an engineer, you have essentially 4 levers that you pull, or you operate at 4 different levels. So not all of those apply to every system. So there are systems that go all the way to running independently as a loop. Some just consist in the first 3 steps, where it's an interactive use of an agent, like a coding agent, where you prompt it and then the harness manages the execution of the task. So the baseline, the base input, which we all know by now very well, is the prompt, right? So this is just the text input that the agent receives directly, system prompt, conversation prompt, etc. Then we engineer context that is woven into the prompt, which often consists in additional data, depending on the task, really, right? Contextual information that is useful for the agent to better meet its target. And that is, of course, an important question, especially when you operate in an environment that is dynamic, where the context evolves and you need to keep the agent current. So that is important how you achieve that. And based on these inputs, the agent acts, and its actions are constrained by the harness, which really is everything that controls its actions and defines how it interacts with the environment. So for instance, what kind of tools can it use? How are the inputs or how are the calls to these tools executed? How are the results processed, etc. Right? So it's the entire operating system for the agent as the information leaves the LLM and returns into the harness to execute the next step or the next steps towards the objective. That, of course, is critical as it comes to efficiency. So first, the overall ability to achieve a goal, do it efficiently, use more or less tokens on the path, and supervise its actions. Trace it, document what it has done so it becomes auditable. All of this happens within the harness, right? The execution of the actions, the the creation of records, and so forth. Now, the idea of loops is the next level, where all of this process, which in itself is a loop, now runs literally on command. So the idea now is that instead of us kicking off the agent with a specific instruction or request, the agent runs on a schedule, maybe to execute a given task. And we'll see with the forecasting agent how that can happen in this context as well. So forecasting agent here is the example that we use. Bridgewater published this example a few months ago. Bridgewater is very engaged in AI. They set up a whole lab for this. Bridgewater is one of the largest hedge funds in the world, if you're not familiar, and it pays to pay attention to what they're doing with agents, because they have invested heavily in this, and there's a lot at stake. So I used this Bridgewater AIA forecaster agent in chapter 24 in the book. This example is Bridgewater's attempt to show that by now, large language models, if equipped with the right harness and the right system, so this is not a single agent, but it's a multi-agent system, that the setup of the system with various engineering tricks and statistical tools and mechanisms, it becomes competitive with humans in forecasting. And it compares the performance on prediction markets of this forecasting agent with super forecasters, which are very familiar by now. So the people that have a specific ability to produce sort of very reliable forecast. And it turns out that in certain environments, this agent that is only able to use web search performs competitively. So that was kind of a breakthrough, given that previous attempts to show this had failed. So what is also useful to have a forecasting agent as a specific example is that we actually get a clear result that we can measure. So there's a prediction that we can measure against actuals. So usually agent evaluation is notoriously extremely difficult because many agents produce output that is at best qualitatively something that can evaluate qualitatively. Even if you take a coding agent and the agent produces a piece of software that maybe meets all the tests, you still may want to think about whether the output is in fact maintainable, whether there's downstream cost associated with excessive complexity, or if there are any other, say, security risks or so that are associated with the output. So often it's difficult to assess clearly whether the output is good or bad, when the dimensions are manifold and the criteria are soft. So here we have a hard criteria because we can measure the actual outcome, and so that's useful. And so this way we can focus on the construction of the agent and then also discuss evaluation without going down a rabbit hole. So now let's look at the 4 components of the decision process. Just like a chatbot, an agent needs a basic prompt. There is a personality. We have 2 types of agents in this agent system. We'll have a research agent that appears multiple times, that has a kind of system prompt that tells it what to do, how to carry out its work, and importantly, when to stop its work, because of course, research is something that you can certainly do forever. So when is information sufficient to make a forecast? The idea here again is a forecasting agent in this example operates on prediction market questions. Kalshi, Polymarket, etc., make available all sorts of questions, and these become available as binary options, meaning they are events that either take place or do not take place, and you can make a forecast. So the system prompt here, sets up the agent with its task, tells it what the rationale is to decide when to stop, and that is more useful than just a hard stop limit that the harness imposes later, which is if you have done X number of iterations, you have to stop anyway, because of course the internal prompt-based judgment may fail, right? But it is a basic markdown file set up to define how the agent would work and what its task is, and then it executes. Now, with the context, it gets more interesting because the context is, of course, task-specific. So depending on what specific type of question we want to answer, and let me show you a few of these examples. So on our website for the book, we have this agent lab where the AIA forecaster runs live. And here you have an idea of what kind of questions these prediction markets ask. Of course, they ask all sorts of questions, but we're focusing on those that have economic relevance because it's a book about finance and trading. So for instance, events include whether the upper bound of the Federal Reserve will exceed a certain value at some point, whether the real GDP growth will exceed or be below some threshold, etc., right? And the market consensus is expressed at some percentage, and then our forecaster delivers some other percentage. So this is kind of the structure of these forecasts. And depending on the type of question, you may, of course, want to add additional information to the question, to the prompt. So, for instance, you may want to add external data, a time series for the specific variable that you're trying to forecast, or other things, right? You may, in the prompt, also want to embed some type of framework, right? So, how do you think about information that you get in terms of how different variables, say, drive the Federal Reserve's actions, right? How does it react to inflation? How does it react to unemployment, right? What are frameworks that we can use? You can provide all this in the context for the agent to use, add this to the prompt, and then maybe evolve this even during different iterations. You can also add skills here. Skills would include such frameworks, for instance, that are task-specific, domain-specific information that allow the agent to address such questions, just like with coding agents, which you probably are familiar with. So this is really where the music often plays in terms of instilling domain expertise into the agent operation. So the harness is all the sort of plumbing around the agent that allows the agent to act, to interact with tools, to interpret the results, how results are formatted, typed, etc. And everything is stored, executed, stored and recorded so that you can ultimately aim to optimize it, because without inspecting the reasoning traces of such agents, it becomes very difficult to get an insight into how specific changes to the prompt, the context, or the harness itself improve the operation of the agent. There are many different task-specific elements here to the harness. So for instance, here we need to incorporate, in order to be able to evaluate the agent, we have to take great care of not using information that wasn't actually available at the time if you want to run this historically. So if you do a web search historically, then of course you risk obtaining information that didn't really exist yet at that point. So you can try to filter out news. So the greatest challenge here when it comes to optimizing and building such a system is, of course, that it's harder to create a faithful historical timeline of how you could have queried the internet 6 months ago or 12 months ago. So optimizing such a system becomes much harder. So you have to build in all sorts of safeguards that allow you to do that to some extent, because otherwise you can only evaluate it going forward, which is, of course, very slow. Right? If you try to build an agent and you have to wait for days, weeks, and months for the queries to resolve, to assess how well the agent performs, it will take very long to optimize it. So harness is essentially the, as I said, operating system around the agent's behavior. And this really is often what drives, what makes the difference in terms of the speed to resolution of a task, and also to the token efficiency with which this is accomplished. And we, in the workshop, discuss in detail the kind of options that you have here to design this. And finally, as we look at loop sort of engineering, we first build a system of these various agents. And the way this system is designed is that it uses multiple research agents in parallel. And here again, you have design options. You can have research agents that are identical, where then sort of the built-in randomness may lead them down different search paths to consider different, to run different search queries, obtain different evidence, interpret the evidence differently, just like human forecasters would, and arrive potentially at conflicting answers. You can also set this up by introducing different personalities and using agents that, in fact, are, for instance, have a bullish outlook or a bearish outlook, so they're optimistic or pessimistic, and use that to instill a debate that may help resolve differences, based on the merits, hopefully. This particular system is designed to have these various agents to generate forecasts. Once they decide that the search is complete, then the forecasts are adjusted potentially for outliers, etc. But most importantly, if a supervisor, which is the second type of agent, identifies that there are contradictions or, say, disagreements among these different research agents, then the supervisor itself can inspect the output of the research agent, so not just the forecast, but also sort of the case they are making, and can try to drill down to identify what are the reasons that lead different agents to different conclusions. And then it can try to resolve these differences. And interestingly, Bridgewater found that this setup was superior to various other setups. So only when the supervisor was able to actually take active investigative action, so to say, to understand what drives different reasons or different predictions, and to try to find additional evidence to sort of find out who is more likely to be right. Did the system as a whole, the ensemble as a whole, improve? So that in the end gives you an overall forecasting system, where, as I said, you can have debate. There are also additional statistical techniques to counteract certain tendencies of LLMs to sort of hedge their forecasts and to be overly cautious and so forth. So there are many additional bells and whistles to how you build such a system, but essentially it's a system that allows you, with a query that comes in, to automatically kick off a research process that produces a forecast. And that, of course, is something that you can run on a schedule. So whenever you need the forecast, then you can kick it off. Whenever new information arrives, you can kick it off. So different ways to utilize this. Now, of course, the main takeaway here is, or the use case for such a system is not so much on a standalone basis, but as a system that feeds into a larger, for instance, trading system, right? Because it's an elegant way to process unstructured information from the web with respect to specific outcomes in a structured way on the fly. Right? So that's kind of how this is used. Of course, also, the way this is set up is that we use web search for the main part. For the workshop, we expanded the system so that you can use third-party data and that you can also use your own questions to answer. So now the benefit is, given the recording of traces and so forth, you have the ability to audit and understand everything. Everything is time-stamped. There's no black box. It's very clear how the agents operate, so you can operate on this basis. And through much optimization, Bridgewater arrived at a system that actually achieves super forecaster parity in certain questions in certain environments. Excuse me. So, and you can then also, through ablation studies, show what the driver of these of the performance gains are. So, so the main drivers here that help really is kind of the overall setup, right? So the design of the agents, interestingly, having identical agents works much better. But as soon as you start changing this, performance potentially decays, right? So you go back to kind of the question of prompts, context, harness, and then the overall loop setup is kind of a good way to get to solid performance for such an agent system. So what do we do in the workshop? In the workshop, we work on a existing repo. So this is the coding agents repo, where you build essentially the system that currently runs live on the website. So in addition to the sort of basic ingredients, which is the Python-based loop that runs the agent, calls the LLM, runs the tools to call the web, access additional data, either gets questions from prediction markets or uses your own questions as inputs, and then predicts its probability that the event will take place or not, as part of the entire system, with given number of research agent and the supervisor to kind of split ties or to intervene. All of that system, together with the production deployment, is kind of the subject of the workshop, going through the prompt, context, harness, and loop stages, and at each stage discuss in detail what the options are that you have to design such a system according to your design choices. Now, the beauty is that the overall system actually applies much more widely. I realized that only when I taught the first workshop, that where the focus was more on forecasting and finance, that actually this is more of a topic of generic agent engineering, because the overall design of the environment for the agent is decisive to make it successful. And you can see in this case very well how different design choices, because the research paper analyzed so many different setups, how different choices actually improve or not the performance, and generally which choices you have available, which is important if you want to engineer your own agents in this context or a different context. So that is the overall message here. And there will be a workshop in just a few days, next Saturday, for those of you who are interested. That leaves us with a few minutes to answer any questions. Does anybody have any questions about this, the workshop or the agent, how it works, or the book, or anything else? Well, I hope to see some of you in the workshop on Saturday. If you have any questions, don't hesitate to reach out and ask. Happy to discuss. And thank you so much
Stefan, I think
Yes.
there are a couple of just questions in the chat. Just wanted to draw your
Oh,
attention to them. That's all.
oh, thank you. Let me see. Okay, so the GitHub repo is private. That's for the workshop attendance. Claude Code is a harness. Yes, Claude Code is a general agent that has a harness that you can also run as a loop, right? There are these new goal commands that you can use to set the agent off on a goal hunt, and then it will just continue to iterate until it achieves that goal. So you have actually the ability to create a loop yourself using a general purpose coding agent, right? So the difference between what we have here and sort of a coding agent is that here we built an agent from scratch, right? If you look into the Codex repo, then in Codex you see Codex is open source, right? So the OpenAI coding agent. There you can see the full kind of setup for the entire harness and agent itself, right? Claude Code leaked at some point, so you also kind of get a sense of what this looks like. Um, so that's essentially how that works. When you say, can you share a live example of this other than trading? You mean as a use case for such an agent, maybe? Okay. So let me explain, right? So here's again the question, difference between harness and loop. So the harness is just any agent that runs needs a harness, right? It's basically the message comes out of the LLM and it has to kind of, there has to be something that receives the message and translates that into a tool call, right? That's the harness, right? How do we format the message that goes into the tool call, all of that, you know? How is the interaction stored and persisted? Is there something that counts how many loops, iterations we already have done? What do we do after we ran 5 or 10 or 15 iterations? Do we stop, right? So basically everything that governs the actions inside the loop over time, right? So you can literally think of this as the loop as something while goal not achieved, do, and then it runs. And then inside you have, if this happens, then do that. That essentially is the harness. The loop is just, and that's why this is confusing, is that the agent, which itself is a loop, can be run sort of as something that is not triggered by the user, right? So the idea of this loop design is that you design the loop so well that you do not need human intervention anymore to either trigger it or tell it to stop, right? All it needs is it needs to receive the definition of a goal that it should achieve, such as build the following software product that has the following features, and here's the definition of when the build is complete, acceptance criteria, tests that are working, etc. And then it will go off and it will run its own loop many, 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 many times. And that is the design of the loop, which includes the harness, right? But also the prompts and everything, right? It's the entire system that runs until hopefully the task completes successfully. So this architecture does not run on Claude or Fable. It calls an LLM of your choice. So it can call a local LLM, say anything via Olama. It can run with DeepSeek, or you can call, an OpenAI or Anthropic model of your choice. So that's a matter of how much you want to spend, essentially. Of course, has performance impact, but that essentially is the impact of cost, right? So you have many different options how to run this, but it's not Claude Code that runs it. Claude Code may help you to build it, but it's not what runs it. But you could run it with Claude Code, right? You could absolutely have the LLM that gets called be a Claude minus P, prompt. So a headless Claude instance. So can you write an agent which orchestrates the task and manages sub-agents? So it depends a bit on what exactly in which context, right? So Claude Code as a general agent is capable of, it has tools, right? So what the agent needs is a tool that allow it to spin up agents or to call other agents that are somehow defined, right? So if you have a library of agents, that do certain tasks, then one agent could, when it decides that the right call for a tool is the agent tool, then it would just spin up that given agent, and the agent would then do some task, right? So you could have this entire multi-agent forecasting system could be a tool for some other agent that maybe wants to, that is a trading agent, right? Say it's the portfolio manager agent, and that has the research question, how likely is it that the Federal Reserve tomorrow is going to raise or lower interest rates? And then it sends off the given agent that we saw just now, and it maybe comes back with an answer. Yeah, I would also say, so there's a question about how to run a loop today. Not everything is if it, so a loop would be monitor my account, and every time there is some activity, respond sensibly, right? That would be a loop. So you monitor your GitHub repo where you participate, and every time there's an issue where you are tagged, then the coding agent acts. That would be the loop design. The trigger would be the tagging of you or the agent or so, and then it would repeat forever. Good. That looks like the questions here are so far answered. Good. So thank you for your attention. If anybody has another question, now is the time to ask. If not, then again, I would love to see you in the workshop on Saturday. If not, thank you for your time and attending this session.